my name is Elder, and this is Martin. We're here today to talk to you a little about iOS 11 and especially the new functionality that is augmented reality. So before we start, a little introduction about ourselves. Like I said, I am Elder. I work at eSailors here in Germany since the beginning of this year in January. I'm Portuguese, so before that I was in Portugal, and I've been working as a mobile developer and software development coach for the last 15 years. And this is Martin.
Yeah, my name is Martin, and I'm working now as mobile developer for almost 7 years. I'm with eSailors now for more than 1 year, and actually my background is mainly gaming, but it now shifted to e-commerce, and that's why I'm interested in ARKit, because it fits perfectly into both worlds.
Okay, so part of our jobs at eSailors are developing mobile apps, but we do other things. So we develop everything from simple Alexa skills to fully fledged, heavy-duty native apps, both for iOS and Android. And part of our job is also always taking a look at new technologies and what's out there and seeing how we can apply that to our products. So when iOS 11 was released, we were really excited, especially with the new ARKit, and we decided to challenge ourselves with a few projects and just see what we could learn about this new feature, so we can later introduce it into some of our apps. So, what's new in iOS 11? There are actually a few things. So augmented reality, of course. Machine learning is also one of the main features of the new SDK. And then Music Kit, SiriKit, and a lot of improvements to other functionalities. Augmented reality is, of course, the one that really caught our attention. Not just our attention. If you look online, you probably already seen there are a lot of experiments, a lot of cool stuff is being done right now. It's a very good time to get into augmented reality, and we're going to talk today a little bit about our experiment, about the basic functionality and some experiments we did while we were learning to work with ARKit. So it is a very high-level API, so it's very simple to use, but it does not do much on its own. So you always need a 3D rendering engine or something that will help you to just get stuff on the screen. Apple has done a great job of providing also this functionality. So we will use Apple's SceneKit mainly to show you how we can add 3D objects to the real world with ARKit and SceneKit. So this is us working on the project. Something we learned is that people will look at you very funny when you're working on AR, because you're always going like this, and people are like, "What the hell is going on?" So we decided, okay, so let's get out of the office for a little while. We went to McDonald's. It didn't go any better. People were just, okay, what's going on here?
Exactly. So after a half hour, I just suggested to leave the place because, with the camera we were watching for detecting stuff, and we're facing the camera in front of people, and people are really not used to that, so they look really weird at us.
So we're going to explore a little bit the world of ARKit, and to start, Martin will just show you the principles of augmented reality.
Yeah, thanks, Hedda. So when we talk about augmented reality, I just want to think about what it is actually. So what does augmented reality bring? And I found a quote on the internet which is really cool, which says, augmented reality is the illusion of virtual objects fixed in real position. So what does that mean? How is this illusion being created? So it's kind of simple. We take a camera video from the real world and we put some 3D stuff on top of it, and the illusion of placing a virtual object in the real world is just be created by moving the virtual objects accordingly our movements. So let me show you a little example. Just go ahead. So here, for example, we have a door, as you can see, and this door has been placed in the real world on a fixed position on the street. And it's even better because you can enter it and you can see a virtual world in real size. That really gives you the impression that you enter another world just on the street. How awesome is that? Another cool example is, as I said, the fixed positioning is one thing that creates the illusion. Is that if we add physics, it literally looks like we're throwing real balls in our environment, for example, like our living room. So, just to sum up, augmented reality is about providing a fixed world in real space. So whenever I move a meter to the left, my virtual world on my device screen is moved a meter to the right. So meter to the right. So this creates the illusion. And it combines motion sensors with video capture. So how has this been done? Actually, as we see here in this video, ARKit keeps track of your video stream. So it looks for interesting points in your images, as you can see here on the laptop, mainly edges, borders, or other interesting points, and keeps track of them. And with this information moving, you all know maybe the parallax effect, we can calculate some kind of depth. And combining this information together with the motion sensors, we can create a very, very stable environment. So just to show it maybe a bit better, we prepared that also for you for a small demo. So here's the app that we just saw. Just turn on debug mode. And as you can see, as I move the device, these dots will be detected. And if I go back a bit, hopefully. It's always a bit, how to say it, relies maximum on there we go. So as you can see, we have some kind of origin point that just stays at the same location. So this gives us somehow the illusion that the world has been fixed. So Hedda is going to tell you more about the positioning.
So, here we go. This is how ARKit actually takes care of everything Martin just told us about the feature points and generating an high precision motion and rotation vector so that your actual device is always in the same relative position compared to the world you are in. So how does world tracking works? World tracking is about position and orientation, about physical distance. For those of you who have 3D experience, we usually use virtual units. So with ARKit, every unit has a very specific physical distance of 1 meter. So whenever you're working with ARKit, and you say, for instance, this vector has 2, 4, 6, so it's 2 meters, 4 meters, 6 meters. So in ARKit, everything has a physical distance. And this works very well because ARKit, by default, also zooms in and out your 3D models, so they always look at the correct distance from your device. So they always have the right size. So, and it's always relative to a starting position, and we have the 3D feature points, like Martin just explained. So I have a little project I will show you. So this is a little bit about how we achieve an AR world. For those of you familiar with iOS development, this will be very easy to understand. For those of you who are not, I will try to make it as simple as possible. So when you have an iOS application, you usually have something called a UI view. which is a rendered object on your phone. It can be a button, it can be a table, it can be a text, it can be pretty much anything. And Apple, that's an iPad, and Apple, and Apple was nice enough with ARKit to just add 2 new views we can use. So they are called AR SceneKit view and AR SpriteKit view. So SceneKit and SpriteKit are Apple's technologies for rendering 3D and 2D content on your device, and you can use ARKit with both. And out of the box, you have a AR SceneKit view for 3D content, which you can also add 2D content with a few changes, and AR SpriteKit view where you can render 2D content on the real world. So I just created a very simple layout for our application. We just have the debug button, and then we can create a cube, create a tank, and then just some stuff I'm going to show you. So how does all of this work? I will just zoom in. Sorry for this. Just 1 second. Presentation. Here we go. So, here we have a reference to our AR view, and as soon as we start our application, I'm just telling it to show us the statistics. This is just some small information like frames per second, and it will just render a few lines so we understand where everything is positioned. And this is where the real magic starts. So ARKit is a session-based API. So we need to create an AR session, and everything we do is controlled by this AR session. So what I am doing here is I'm creating a new AR world tracking configuration. This is the configuration of the session, and then I am running this session with this specific configuration. So every time you run a session, you need to give it a configuration, and you can configure pretty much anything you want regarding your AR world. So for instance, what I'm doing here, I'm just giving it a world alignment. And what does this mean? So when you are in ARKit, like every 3D world, you need a point of origin. Okay, and the point of origin in ARKit is always the position of your device when the session starts. So for instance, here, when my app will start, the session will start, and if I have my phone here, this will be the origin of my world. So 0.000, and the XYZ coordinates of my world will be this here. So if I move my phone will have a relative position to the origin point always. And the origin point will be maintained by the tracking capabilities we discussed earlier. So this is the position, but what about the rotation? When you're in 3D space, you don't only have a position, you also have a rotation. So you have 3 options here. You have the camera rotation, so the X, Y, and Z axis will be relative to your phone position. The default, if I'm not mistaken, is gravity. So Y will always be pointing up, so it's always parallel to the Earth's gravity. This is achieved by default with your phone's motion, and my personal favorite is gravity and adding, which means that the Z-axis is always pointing south and the X-axis is always pointing west. So no matter where you are, your rotation is always the same compared to other devices. So every device is pointing south and west and pointing upwards for the Y-axis. So what we did here was a small application, and I will show you the application and then come back to the code to show you how we achieve this. This is the first application we tried. So to really understand how AR works, I'm pressing escape instead of doing this. Here we go. So like Martin already showed you guys, let me just unlock the phone. Don't look at my password. So like Martin already showed you guys, I can just turn on debug mode, and you can see all the feature points that are used, and somewhere we should have, there it is. This is our world origin. So the phone was here when we started the AR session. And I can tell you that from this, so that is west, that is south. You can check on your own on your own devices, but this is pretty accurate, and I'm pretty sure that is up. So we're safe on that side. So now what I'm going to do, I just have 3 buttons here just to show you some of the things we can do. I'm just going to add a cube. So what I did, I'm adding a cube always relative to the camera position. So I just calculate the camera position and I place a cube just I think it's 1 meter in front of the camera. We will see. So here we go. So I have 1 cube here, and as you can see, the cube stays stationary in the world. And you can just pretty much, so this is why people think it's weird when you're working with AR. So you can just see that this cube is here, and if you're sick of the cube, you can just explode it. So we can. This is a very easy thing to do. So this is just a scene kit primitive. So we just designed the cube, but you can also do this with more expensive rendered materials, like for instance a tank, and here you are, just a little 3D tank that you can use. So how do we do this? I'm just going back to code. Okay. So I'm going back to code, and here I just have the touches began. This is just some simple iOS stuff to detect when somebody clicks the screen, and I'm just getting, oh, this is not what I wanted, sorry. I want the clicked cube, sorry. So this is the clicked cube function. It is called when we press that button, and what we're doing here is we're creating an identity matrix, and we're placing it, the z-axis, 1.5 meters in front of us. So like I told you before, these units are always in meters. So I create this, and then I create some simple cube geometry, which has 20 centimeters in length, and then a chamfer radius. That's just the edges, the rounding of the edges, and then we just add some material. So these are just some simple images, so we can have the ABC cube instead of just a colorful cube. So then we just multiply the matrices. I won't get into algebra here, so we can talk about it later if you need to. And then we just add this simple node to our scene view. So the root node of our scene is the origin point. I place this in front of the camera. So first I get the camera position. Basically the frame gives me the position of every, gives me the position of the camera on every frame we use. So since this is triggered when we click, we get it when we click. And then I just did something else. It's like, did the same with tank. And so we can explode, I just added some particle physics in the same position as the cube. So I just remove the cube and I just explode, just do some small particle physics. The code will be available, and we can talk a little bit about it later. So these are the basic, I'm always pressing escape, sorry. These are the basic principles of the positioning and world tracking, and now Martin will continue with plane detection.
So as we saw in the examples from the very beginning in the video with the physics, we saw that the balls were dropping on the floor. But actually, the problem of the word positioning that Helder described is, where is the floor? You know, if we have a point in real space somewhere where our device has been when we started the application, right? We need to somehow detect where the floor is. And actually, ARKit is providing us some functionality for that, which we're going to show here in another demo. We prepared a lot of demos today. And the main reason why we did this is also we have a little game at the very end, which we want to show you. And we want to move some, you know, tanks. So here we go. That's our app. We just turn off the level for the moment. So as you can see, as I move my device, the floor has been detected by ARKit as well. So we can enable floor detection with ARKit and move. And also we have different levels. You can see if its work depends mainly on the lighting conditions and on the textures. So if we have a texture like this nice, Decke, whatever it is in English, you can see we can detect it. And you can see if I go down, right, you know, it perfectly aligns, almost perfectly aligns to the floor. So this gives us the capability to, for example, just turn on levels, place a level on top. So what we've done is just have a level, you know, we calculate the floor. So if we make a bigger floor, our level scales accordingly. And the applications for that are huge. I just noticed yesterday, IKEA brought its app. So you can place, for example, furniture to look how it looks in the real world before you make your purchases. Or you can just create game boards in the real world and play with your friends. I don't know, our tank game maybe. Or Mensch ärger dich nicht. So back to the slides. So how does the plane detection work? I previously talked about the feature points and their detection. And if we have multiple points in the scene, you might notice if you look out of the window when you're driving a car, hopefully you don't do this while driving, you see you know, objects that are further distance are not moving as fast as objects that are closer to us, like this. So with this information and the movement of our device, ARKit is just able to detect planes. ARKit is not only for plane detection, we can even detect more things. So with the new iPhone X upcoming, there will be a new configuration for face tracking as well. So ARKit will use the same techniques described before to just raycast your face with infrared light sensors and calculate time with depth. That's something that's missing for older phones because it requires special hardware. But it causes a more accurate depth information map. So how do we turn it on? Actually, we get our planes by listening to a delegate. So we come to the code later. And we got provided by two information. We have AR plane anchor, or in the new iPhone X, AR face anchor if we want to turn on face detection. So AR plane anchor actually gives us the information where the ground has been located and how big it is. So let's drive to the code. So here we have an AR session without any integration to a 3D framework. This comes later. And we enable horizontal plane detection. At the moment, ARKit is not able to detect walls. It just can detect horizontal ground. And then we run the session. And from that point on, we start receiving the delegate method. And this method actually provides us with AR plane anchors. So what we are going to do to create this little floor, we're creating a box, getting the X and Z coordinates. So X is our width actually, and Z is the depth. And give it a simple height. And then we add it to our node. Because now we just have position and a length. But the node that has been created for us has also the orientation. So we don't have to take care of this. So at the end, we save all these grounds and update them accordingly when we move the device, which also gives us the impression that the floor is growing. So now back to Helder for a nice idea about position sharing.
Yeah, so when we started working with ARKit, one of the things we wanted to do was just how do we share an AR session between devices? So ARKit does not provide this capability. What we really wanted to achieve was, so I'm on my device, Martin is on his device, and we want to be looking at the same content that responds to the same movements in each of our devices. So we started thinking, how can we achieve this? So this is relatively hard because, so if he has one device and I have one device, we both have our own origin points. So one way to fix this would be to start our sessions at the same time in the same exact place. This would be a little weird, but in theory, it would work. So what we decided to do was we decided to share our position relative to the world with plane detection. So like Martin said, we can detect a plane, and if everything is working fine, both devices will detect the same plane in the same space. So if I point here with one device, I can get one plane in that specific point, and if I point at it with another device, I get the exact same plane. So this fixes the position, but this does not fix the rotation. So because the devices can be rotated, we can be looking at it from different angles. But if, like I showed you before, if we start our session with a configuration of gravity and alignment, then we can have our devices and our world origins aligned to the north, south, east, and west axis. So then we have two devices with the same rotations, but which are in different positions, right? So what we did is, when we detect a plane, we start our project, a game in this case, and we add an home node. So every single node, every single feature we're going to add, it's not going to be relative to our origin point, but it's going to be relative to this node we detected. And by doing that, we have always the same movements relative to the exact same space. And if I'm looking at some AR content, and Martin is looking at some AR content, could be somebody else, not just Martin, is looking at some AR content, and we make changes and we add cubes or we add some stuff, we can just share this positioning. So we still need to share stuff. That's not part of this talk. We decided for our demo and for our little prototype, we decided to just do some peer connectivity, and we're going to try and show you now how everything works. This is not a finished project, just a small prototype we did, and maybe we can show you how it works. So you will only be able to see one of the screens. You need help?
Something for you?
Yeah, I'll just create yours.
So
here.
I search, you advertise.
Where's the screen? Here it is. Okay. So this is just some peer connectivity, and now we can just try and detect the planes. I've detected mine, and so have you. And now if we start the game, here we are in AR. So I will just move a little bit away. Oh, mine looks much cooler, if you can see, because I'm not anchored by a by a string. And now, can you see my tank? There you go. And now I can just move. We can just try and kill each other in AR. So yeah, this is achieved just by some peer-to-peer sharing. We decided to create a larger world so we could show it here on the big screen. If you're just doing this locally with your friends, a smaller world would be a little better. And You're trying to kill me. Here you go. And yeah, this is what we achieved. It's not perfect yet. ARKit still has a few things that can be improved. Probably it will be on the next iterations.
I think the biggest issue for us was, when we got the contents, we got it from Unity, from a tutorial, so you can also check that out. All the metrics and all the meshes are not sized in meters. So if we put the first meshes in there, they were gigantic, so we were not even able to see them. So we had to go through every individual asset and scale it down. We helped us with a small trick there, but yeah, actually it was really a lot of work to make content accessible for ARKit.
Why are you trying to get me away from the screen?
What's that? Where are you?
That's me.
Just come a bit closer to me, by the way.
And now we're lost. So, this is our presentation. I hope you liked it. Any questions? There's one.
Thank you. Firstly, thanks for the presentation. It was great. Just one short question. Would it be possible to do a ARKit with Metal 2 from Apple as well?
Well, right now we're with SpriteKit, SceneKit, and Metal.
Indeed, it's possible. Apple has also some samples. We haven't dived into that one because we wanted to focus on the capabilities. But what you get is 60 frames per second information about all the details that you need. So you get all the information. I'm not sure if Apple directly integrated it into Metal, but in case not, you can simply just apply the vectors to Metal and then you're fine.
Yeah. Also, we're not just we don't just have to live with Apple's technology. So our presentation and this code was done with SceneKit, but either Unity or Unreal Engine, which are a lot friendlier from my point of view for game development, are very easy to use with the ARKit. So you have Unity and Unreal plugins and assets, which you can very easily use. So I think there was another question upstairs.
Hi, does ARKit provide any information about the lights from the real world to maybe cast shadows or something?
Yep, so you get ambient lighting information according to the real world. You can configure AR to track this, so will be tracked by the images you receive. Yeah, it's possible.
How about Xcode? So you said there are 2 new views available.
Mm-hmm.
Are there some kind of sub-views like up to now there is, for example, for a table view you have an own view, or you can have it as a sub-view. So the question is it like a sub-view, and if it is, how easy is it to add other controls?
Yeah, we did that with the sample projects, as you might notice, so the UI switches. So you can either run AR scene as your view controller's view, that's possible, but you can also add it as a sub-view, even in limited frame. So you are not required to have it full screen. Apple solved the issue by using in AR frames normalized vectors. So when you get AR frames, you get positions in a normalized way, which means from 0 to 1. And then you can calculate the exact pixel positions of your views, height and width by using these vectors. So for example, if you have 0.5 vector, means you have half of the size of the screen. Other questions?
Will this work also outside of a room, in nature or something?
Yeah, that's a good question. Definitely better than here because the lighting conditions are not so good. So it depends mainly on the lighting. The term work, I would split it up a bit because what does it mean? So work means that we have a flat ground somewhere, right? Because we overlay 3D objects on top of the camera image. So if I, for example, detect this plane here, but I have a bottle on top, of course you won't see the bottle, even if that will be the right information. So there is no auto cutting or culling feature that would enable this. So you should have flat environments.
But to answer your question, like we showed before, all the tracking is based on feature points. So the more feature points you have, the better. So if you're outside and if it's during the daytime, and for instance, if you're in a park with trees, so you have a lot of feature points, so it will work very well. If you're just pointing at the uniform setting, like a wall with no patterns, just a blank, or in this case, a red wall, it will work very badly because it won't be able to capture any feature points from a uniform frame.
Maybe in small addition, of course, you get information about the tracking state. So ARKit is telling you whether the conditions are good or bad. And there's also some hints from ARKit that you can provide to the user to solve it. So you can actually tell the user
just go somewhere else.
Yeah, yeah, exactly.
You showed an example where there were balls shooting at the door and the wall. How this is possible? You said it's only possible to detect the plane.
You mean this one, right?
Yeah.
So actually, the developer of that video has done a fantastic idea. So he let the user set up vertical planes by just selecting points. So you use the app and then you select just points to create vertical planes. Pretty easy.
So if you see the full video, you will see that before this, you're just dragging and selecting your own virtual planes manually.
But we hope that Apple is coming up also with an automated solution because, of course, it's not a good user experience. More questions? Then that's it. Thank you very much, guys.
Thank you.